So let's start. Last time our theme was spin polarizing calculations, and we have considered spin systems with parallel spins. So, systems with parallel spins, they can be rather rather hard to calculate, rather hard to solve, and rather difficult for their structure. And today we are going to talk about non-collinear calculations. So what will happen if we will allow spins not to be or not to have only up and down sides, but every side which which it can take. So today we will consider non-collinear calculations, and I'll show you the effect which calls spin-orbital coupling. So what is this effect? This is effect. It origins from quantum nature of our materials. So we have some atom with this purple ball. Some atom, it has some magnetic momentum L, and we have some spin. It has some spin moment S. Yeah, and they interact in some way. And we see that if we just will take these vectors L and S, so we can add them, and we will get a resulting vector L plus S equals G. So this will be the momentum vector of the system. And in the case if spin will be just up and down, so if it will be parallel to our magnetic moment, we just have L plus S or L minus S, and it will be easier. But here we have some non-collinear. Here we have some non-collinear behavior of spins of the spin system. And what happens to our bond structure? Bond structure, if we will allow our electrons behave like this. Okay, they behave like this in nature usually, but in the calculations it take much more computational time to include all these effects. So that's why we include these parameters only if you want to make very, very precise calculations. So what happens to band structure? We have some degenerate level. This is level N2, L1, so it's like some p orbital, magnetic moment 3 divided by 2. And if we will allow this spin orbital coupling, we see that why it calls coupling, because we see that this degenerated level will couple in two levels. So we'll have one level and another level, L minus S and L plus S. So this vector. And this splitting is rather tiny effect. You will see today how tiny is it, but in some systems it can be very very important. So if you want to go deeper in the electronic structure. What about formulas? So here is spin orbit coupling term in Hamiltonian, and we see here is some constant electron mass, and we have this vector. So we have Pauli spin vectors just to deal with spins. And we have some Kohn-Sham potential. So this is our band energy. And P is electron momentum. So what happens here? How do you think? What is the what condition should satisfy this formula for this effect to be visible? So what should happen to the structure, to the system, for us to see this effect? Because this term is rather small, so it should be more or less visible. what should happen to our electrons or atoms? How do you think? You see here is quantum potential, some just Pauli matrices, and electron momentum. Yeah, momentum should be large. It means that our electrons should be very, very fast, and it means that we should work with a relativistic approach. This effect will be visible only if we use a relativistic approach, and it means that we will use for first in our lecture, in our seminars, we will use relativistic pseudo potentials to see this effect, because for non-relativistic, this effect will be too small, too tiny, and we will not see it. It will be tiny even with relativistic, but we can see it with relativistic electrons. How we can include relativistic? This is a slide from last term's presentation. So here is our quantum potential. So it's some external field which will be approximated by pseudo potential. So we use pseudo potentials. There's Hartree energy and exchange correlation. So we know how to deal with all these things. Exchange correlation, we will use PBA. We will use some pseudo potential to treat this field. And we have also this term. This is kinetic energy term, and it can be non-relativistic. Usually we use scalar relativistic. It means that we solve not Schrödinger equation, but Dirac equation, but without this term for spin-orbit coupling. But if we will use a full relativistic approach, it means that we will solve Dirac equation, but with that spin-orbit coupling term, which I showed you before. And this only one term, it takes rather huge amount of computational researches, and you will see today from your output what happens to it. And we will use these potentials. So here is, yes, rel PB is so is better. So rel means relativistic, full relativistic kinetic energy approach. And before we use scalar relativistic, so we can use it by default. By default, it's scalar relativistic. It's better than Schrödinger equation, Dirac equation, but without spin orbital coupling term. Only one this term requires a lot of calculations. And I want to demonstrate to today this this effect, spin orbital coupling, and we should do two sets of calculations. One set, it will be just common calculations for gallium arsenide, and another calculation, it will be spin orbital calculation. So spin orbital coupling, SOC. I call it SOC. And we will do this, and then we will compare what we'll get. So what bands, so we just band structure equations. So what bands we'll see. And it's this effect, yeah, by doing like this, we are going deeply into electronic structure for some particular structures. Then we can do it by our default calculations, which we provided before. So we should use MP 2534 because it's a lot of gallium arsenide. We should use this 2533, 34 because it's the lowest. It has the lowest energy. Yeah, maybe we can. We should copy the pseudo potentials. And we should take two different pseudo potentials. So I propose to take PBS just common for BSO and relativistic for BSO. You see, they're identical except for rel. Not this. Yeah, you can copy regular if you need it, and then relativistic. Yes, relativistic по BSO, yes. I'll just copy it.
What would you suggest? Create different folders for relativistic and non-relativistic case, or just?
We have by default. So I gave you lab 13 in the in chat. Oh, I didn't do it. I think maybe I forgot it. So I can do it right now. Maybe I forgot it. Yeah, I forgot it. Oh, here it is. Yeah, I proposed to do to make two different folders just for common calculation and for spin orbital calculation. So we have the structure, yeah. I browse LDM, number of atoms, type of atoms for spin orbit coupling. And we see we have it's a little bit tricky thing. We have cubic structure for gallium arsenide. You can go down to the structure. Yes, crystal structure. You see we have a cubic system, and primitive cubic system, it has 8 atoms. And if you will copy 8 atoms for for this Pascal, it will contain 8 atoms, and 8 atoms is rather huge amount even for cluster, so it will take some time to create it. But this cubic system, it usually have conventional cell. So this is conventional cell. It's huge and it has primitive with only 2 atoms. I can show you it. FCC primitive. FCC primitive cell. You see, yeah. This is our conventional cell with 8 atoms, but we can reduce it to a primitive cell with only 2 atoms in unit cell. Yeah, and we can for FCC it will be the same for all these FCC structures. For silicon, we started from silicon. For a diamond, for gallium arsenide, it will be the same. So it has 2 atoms, one with 0, 0, 0, and another with 0, 25, 0, 25, 0, 25. So we will have 2 coordinates. And we had to choose eyebrow. You see, we have 2 eyebrows for cubic, even 3 eyebrow for cubic. We have cubic P. It means that we will use conventional cell with 8 atoms. So A, B, C, we see, you can see this is cubic 1, 0, 0, 0, 1, 0, 0, 0, 1. Then we can use cubic F this is our case. It will take rather harder vectors, but it will take these vectors. So it will take these vectors A, B, C. So these vectors V1, V2, they are Z vectors for primitive cell. And cubic BCC, it's another case for not for FCC, but for volume centered. So now we had to use F second eyebrow. You have calculated it for units, yes? No. You see, we had to use not this vector. You already use this primitive, yeah? You should use conventional because eyebrow will automatically convert it to primitive. So you should use conventional. And eyebrow will automatically do it. So it's like 10. 1086, 59, 24. I also want to follow you. How it was? It was 10, 89, yes.
659.
24. Yeah, okay. I hope you got the idea for, which stands for this cubic systems. So if we can use this primitive cell because primitive cell usually has less items. 2 and 2, you cut.
What about
You can check.
yeah.
Relativistic, yeah, we use relativistic pseudo potential.
16.
16.
We can choose 9.
Yeah, maybe 90. I used 80, and for 80 it took 14 minutes. So maybe even better for 80 because it will take more time. Atomic species, yeah, we have Gary and Zenit. $69, 723. And name of what about arsenite? What atomic mass does it have? So you copy it here to the folder. $92.16. Yeah, but we don't need all these coordinates. We just need in this coordinates we also don't need. First three coordinates, it's like first three vectors, it's a cell, and this coordinates of atoms. But for primitive cell, we don't need all these atoms. So with primitive cell, the story about primitive cell that we can use not 8 atoms as for conventional this big cell, but we can use only 2 atoms, which will satisfy this small cage, and we can calculate it. And iBraf2, it provides it. So we can type A, it's cell DM1, or it's this parameter this parameter for conventional. Yeah, and then iBraf2, if you choose second iBraf2, it will automatically transfer it to the primitive cell. But you have to type different coordinates. So your coordinates will be like 0, 0. It will be all 0 for one atom, and 0, 25, 0, 25, 25 for another atom. This works for only for cubic FCC systems. So you should pay attention. And some key points. Yeah, I think it will be enough. I used 888, but maybe 666 is better because yeah, for relaxation it will be okay. And it looks like we have filled all the gaps, so we can start calculation. So Igor, you can cancel share screen, and I want to say a few words about that parameter. So we had two new tags here. We had L spin orbit and non-collinear, true and true. So what does it mean? L spin orbit and non-collinear. Let's get what is it. Is non-collinear, so it means non-collinear spins. This is what about I told in the beginning of our seminar. You should allow spins not be collinear, not be parallel to atom moments. This is very crucial for our this is very crucial for spin orbit coupling, because here, so this effect, it arises only we have this spin collinear, non-collinear spins, which will be not parallel to the atomic orbit. And also we have another parameter which calls spin orb. It just also have two values, true or false, and it allows us the calculations of spin orbital coupling. I should find it. Spin orb. Yeah, here it is. So this tag, it also has only two values, true or false, and it allows us to calculate this spin orbital term in relativistic pseudo-potential. So this is, they are very simple. Non-collinear, we allow non-collinear calculations. We allow this spins not to be collinear to our atomic moments. And L spin orbit, it means that we can we allow spin orbital calculations, spin orbital interactions. It includes that that term into our Hamiltonian for spin orbital coupling. And now we can do the same for normal calculations. Your calculation is done already. You should take. I tested it for 888 key points, and for 80 it got WFC. So maybe for 666 key points, it is really very fast. I can check. Yeah, I can show you it. So you can check it. These two terms, they add a very huge amount of time and researches. We will compare them. Relativistic, yeah. But maybe everything is okay. So, okay. Start new skill. I see two processes in short queue. So one of them mine. You have problem. And what don't work? I just copy all the data. Maybe even we can. Maybe we can even copy. Do the same for relax folder for Gali arsenide, but without spin orbital coupling. Yeah, yeah. Maybe we can even copy that file and then change because they are almost the same. So I just propose to copy it. Rename. Oh, we can make really small changes. So first of all, we should delete these terms, non-collinear and spin orbital calculations, and we will see what will be changed. And another, we should delete this relativistic rel. So we should change only two things. Delete the terms and delete rel here in pseudo potentials, because all other things are the same. And also we had to copy normal pseudo potentials, not relativistic. Normal with Carl relativistic pseudo potentials to the folder. no trail. You can try PBSO. Is everything okay?
No, stop my potentials. It's never be converted to things like
Instead of UPF? Так, зараз покажу. Дивіться, у нас є дві папки, так? GaAs AS і GaAs SOC. В кожній з них є релаксація. Релаксацію ми там вже в GaAs SOC запустили, і там оці от були файли. So you had to do the same, but for common creation, GaAs arsenide in folder relax. And what should you change? You should change really almost nothing. You should delete that two terms, non-collinear and spin-orbital, and you should change here the name of the potentials. You can do it and start the normal calculations, not spin-orbital. In the folder of GaAs arsenide, relax. And you had to notice that we should use the normal PBSO pseudo potentials, not real. And then we will compare what happens.
Question about in general.
Mm-hmm.
Maybe will be interesting. So, what do we need to estimate? Do we really need to do it or not? Just when we have some heavy items with F orbitals, or do we have some other
Yeah, when we so the question is when we need this spin orbital coupling. Yeah, when we have rather huge atoms here, so when we have even d orbitals can give the spin orbital coupling for some heavy items. For f orbitals, we should use it. But sometimes it really so it you will see today that it gives only tiny difference in the energy. It gives tiny difference in crystal structure, and it gives rather no, perhaps for some systems, perhaps for some experiments, we need to calculate the spin orbital coupling and check how this bands coupling. Yeah, but usually it also gives not huge difference. So if you want to what I saw in the papers, people usually tell that we have calculated energy with spin orbital coupling. We have calculated for normal calculations. We see that the difference is negligible, but spin orbital coupling gives 10 times more researches. That's why we will just use normal calculations.
Whatever we have calculated the energies, is it perform the relaxation or the entire SCF?
Relaxation, yeah, relaxation then SCF. So I mean energy which you get for after SCF.
Also, I think you should probably explore it. I read in documentation something that states that by default, Quantum Espresso after relaxation, it conducts a SCF cycle.
Conducts one SCF cycle, yeah.
So potentially we might just do separate SCF.
I usually do separate SCF because then we should copy the folder and copy the XML file to the NSCF and to band structure. So if you just want to collect the energy, maybe yes. But if you just then need to take the folder and to the functions, I usually propose to make SCF.
But it still generates safe folder and XML file.
I think okay, you can compare this SCF from relaxation and SCF, the common SCF, and I don't know why, but it will show different, slightly different energies. I don't know why. And usually, for relaxation, we also use not so huge number of key points. Because we want to speed up. And then for SF, we can increase, for example, YKWC, we can increase this number of key points, and that's why it's useful. So that's why it's useful to make SF after relaxation.
How much time did your spin-orbital coupling take?
8 minutes. So maybe we can sub here. So have you started the common calculation? It stays in the. I see 4 drops in short. Okay. We can see the difference. We can see the difference in the files. I will open spin orbital coupling output. What I want to see, estimated total dynamical RAM. It's like 636 megabytes. Yeah, for 2 atoms. We just have 2 atoms. Usually it takes like less than 100, maybe 40 or something like this. And we can check what happens to common relaxation. And it will take, for the same system, 221. So it grows the researches 3 times. But it's not the limit. So usually it can take even more, even more, because here we have only 2 atoms. But if we have a lot of atoms, so we will have much more interaction between these atoms, much more. The system will be much more complicated, and that's why 3 times it will be not. So we will have gigabytes of this estimated total dynamical RAM. And also the time of calculation. So I think that just common relaxation, it will take not 8 minutes, but it will take maybe a few minutes, maybe a couple of minutes.
Something like uranium oxide, let's say, where uranium has a lot of really heavy fermions, I mean, the F orbitals and so on, and oxygen is just oxygen. So in the 1 atom,
so what happens if the system? What happens if the system has 1 heavy atom and not heavy? We allow these parameters on collinear and spin orbital for all the systems. So we don't specify the atom. For this huge atom, you can maybe add some U, if you want to treat some F electrons, the screen. Yeah, but usually it's not usually we use for all atoms. Oh, because for example, oxygen can interact with this huge atom. Yeah, and you have some combined orbitals maybe. So this is important. So this is important to do it for them. We can create maybe the folders for SCF calculations and for bands calculations, because we need to do it. So we have relax, make dir SCF bands, and maybe we can copy the files for spin orbital coupling, because it was. I think that for spin orbital coupling, we can create a CF file. So I copy from relax folder, I copy in file in. And I also copy the pseudo potentials. And the script. So the four files, if you need to. And what I also need. I had to check the structure. Final structure parameters was like this. So this is our final structure parameter, which we'll use for SF calculations. 6.9, and then we will compare it from for common calculations. You're finished. Yeah, so you can create this SCF file. This SCF file. I propose to rename it to SCF SOC. SCF SOC. And then we had to edit it. Calculation type. SCF calculation. SCF calculation. Then I just delete this stuff because it's only for relaxation. Okay, not only for relaxation, but it's useful for relaxation. And here I can write verbosity equals high. Relax in. So we are working in relax. We are working in Spin-orbital folder, and from relax I copied just file in to SCF. And I also can want to rename it and change VC relax to SCF. Two pseudo potentials script. Then from file from relax out, you should take the final CLDM, the final structure. I already filled it for me. And that's all. So it's the maybe we can use mock points. So maybe it can be 8 points. So tell me if we finish this. You see, you should delete that stuff after pseudo-dir in control and change it by you wish to verbosity high. Then you should delete also these things, cells and ions, because we need it for relaxation. You should delete all the text after pseudo-dir in control. In control, after pseudo-dir, we have 4 texts. It's some relaxation stuff. Yes, ions and cell. Yeah, and you should take CLDM1 from relaxation. Yeah, I think they will. Okay. Yeah, that's great. So we can do the same for the common gallium arsenate. All the same things. So you should change from you should copy from relax. We see relax. We can rename it. We can rename it to SF in. What else? Set the potentials. And also the script. And make the same changes. So calculation, we should change to SCF calculation type. Then we can delete this, all the stuff with forces and energies. And optionally, we can write verbosity high because it will give us a lot of useful information. Verbosity high, then I will change key points. And also I had to copy, so I had to change CLDM. So I will take it from output in relaxation. Yeah, it differs. It differs. It differs, but it differs not so hugely. Of course, it differs. Yeah, you should go to relax out and take sodium.
Oh, yeah, differences in the fish I misremember. What is that? Previously?
It will, I think this SF version will take like 20 seconds. For socket will be slightly more, but for socket 2 minutes, yeah? And don't forget to change the script. And then we can compare the output of both of two SFs. So we can compare these two structures from to SF. I can compare the output from them. So to the left is normal calculations, and to the right is calculation with spin orbit coupling. What we see here. So what's the difference? First of all, the difference in structure. Yeah, we got the structure from relaxation, and we see that for normal calculation it's like 6958. For a spin orbital complex, it's 6985. The difference is too small. So in some cases, maybe this difference will be really meaningful, but for our structure, so we can, what I can say that what conclusion we can make? We can make conclusion that we can, for simplicity, just for to save some researches, we can make just normal relaxation without spin orbital coupling, because the difference in the structure is very low. if we want to make, let's say, rather root calculations, yeah, we can skip this SOC option in relaxation.
We have already done it.
Yeah, we have already done it. We have done it to show. I wanted to show you the difference. So it was for educational purposes.
We haven't actually calculated it.
Usually the difference will be very low. Maybe for some structures like van der Waals materials, it's yeah.
Use PDP potential file instead of PDP solve potential file. Our lattice parameter would be 1086.
1086. Yeah, it's huge difference. Yeah. So you made the calculations with PBE, yeah, and PBSO. Yeah, the difference is huge. This what did I say? 86, yes. So 86 and 69 is a rather huge difference. So this is worth to make the calculation for the difference. Then what another difference we have? I already told you about the researchers, and you see that just common SCF for two atom, yeah, we almost 600 megabytes, and here it's 200 megabytes. So so when we just added this spin orbital coupling, it got 3 times more researchers, but only for 2 atoms, only for 2 atoms. What another thing we can see from this? We want to go to the energy, so I want to compare the energy. PBE because it's not so efficient, because when our pseudo potential is not suitable for the structure, it will take more. Yeah, but you see, it's sometimes this is not 100 megabytes, sometimes it's 10 gigabytes.
So does 69
680. Thank you very much. Yeah, not so hugely. Okay, then we see the difference in Fermi energy. It's also not so huge. Yeah, and the difference in total energy. Total energy is like 447 Rydberg, and then 82, and here 1. So we see, and here is 448. So energy with spin orbit coupling slightly lower, but maybe even not slightly. You see, it's like 0.3 Rydbergs. It's rather huge difference. 0.3 Rydbergs for 2 atoms. So this spin orbit coupling, it added 0.3 Rydberg. It changed the structure very tiny, very low. It almost didn't change the Fermi level, so Fermi level almost, but the energy, it is rather considerable. So we can show we should pay attention to this difference. Yeah, but some geometrical parameters, they almost didn't change. So this is energy difference 0.3 Rydberg. It's only for spin orbital coupling.
I'll allow once more for PDP potential for the energy is 629.
For PBE is 629, yeah, not 848, yeah.
0.5 electron volts.
0.5, not 0.3. Rydbergs, not electron volts, Rydbergs. Oh, it's the difference in 0 point. Yeah, you see that PBE gives bigger differences. Okay, so we can do next part of our calculations. We can do band structure calculation. It will be the last part. So it will be like bands. Don't forget to copy the folder. So from SF, I copy to bands folder to do itself. And then I copy our script. Then I copy XML file. And then I copy this file SF, which I will change to bands file. Bands in. Now I'm in normal calculation folder, not in Spin-orbital. Yeah, and pseudo-potentials. I also had to copy the pseudo-potentials. So let's change.
Copy the save folder.
Yes, save folder and XML. Now I want to change this file. It will be like bands. Then what else? I had to add some NBND, number of quantum states, number of bands, and I should estimate it. So I had to estimate it. The number of electrons in arsenide is 5. And for Gali is 13. 5 plus 13, 18. So I should take half and something. So half will be 9. And but okay, for this calculation, I propose to take 20 to show you some things. So it will be 20 in BND. 20. And no, it's not relativistic. But they all will be almost the same, these files. So it's I had to also to fill this point path. So I want to find the path from seek path. And calculate my structure. Usually these cubic structures, they have very difficult, very complicated, this brilliant zone, you see how beautiful it is. But the structure is not so. Yeah, and here we see this primitive. You see, it's not cubic conventional, it's primitive stuff. Because it's created by eyebrow tool. But it tells us that we have this primitive cell, yeah, and we have corrected number 216 space group. Okay, our path. I had to see the path which I used. My tests. Save XML, скрипт, все потенціали. Зараз, секундочку. Гамма X, гамма L, E. Now I want to fill the path.
Not change anything. And Ben's field.
Yes. On BND and Benz. And now I want to fill. You see, here we have this suggested path, but you see this U and K, they two both. What does it mean? It means that we go gamma XU. What is gamma XU? Gamma XU is gamma XU, yeah, and then we jump to K. It means then from U we jump to K. And start from K. This line means that we just jump to it. So it's like here was one part of the path, and here is another part of the path. We can avoid it, and I propose you to take just gamma X K, gamma LWX. So just avoid U, and we will have a slightly different path. So we'll have gamma X K here. So it will go from X to K, and then return to gamma. So it will be this closed path. So it will be like gamma XK, gamma LW. So now we should change the script. For bands. But this time in script we should also use PWX because it's not post-processing. Bands, and I submit it. Yeah, looks like it works. And absolutely the same I had to do for spin-orbital, orbit coupling. I just submitted the calculation. I mean, absolutely the same procedure that you should copy into bands folder. You should copy from SCF, this SCF save, this save folder. Then set up the potentials. Then I want to copy XML file, QS script, and this file in band, and I want to just to rename it Bans sock in. Yeah, Bans sock in. And in this band sock in, I will change SCF to bands. Then I will add NBND, but here in NBND, you should we used 20 for normal bands calculation, but here you should use 40, 2 times more, because we will have 2 times more bands than for normal calculation. And then I want to add our pass. PW, because it's not the post-processing. The number of bands we should change to 40 because each band will be splitted. So we will have not one band, but we will have two bands. And that's why I had to increase it. And all other things are the same, except for this stuff, spin orbital and relativistic pseudo potentials. And this calculation should take like 3 minutes, maybe 4 minutes. I forgot to change. I forgot to change the number of key points between the dots. Yeah. Because it will be too rude, so the port will be not so huge. No, 40 is okay. For me, it was 20. Yeah, if you use 40, that's okay. For me, it was 20, and 20 is ugly. So it will be really ugly. If you launch these calculations bands, we can proceed to post-processing. Now I go to a normal folder. Normal folder, bands. It should be finished, and I want to copy some file for some bands to file. Bands to in.
Total dynamical.
Total
dynamical.
So for post-processing, you should create this file, gallium arsenide bands to in normal folder, in normal, yeah, bands to in. Arsenide bands to in with this. So it is very, very simple. So I will remind you how to use how to put graphics. I go to, okay, first of all, I should take my folders path, then I should go to some node, let's say node at 29 PWD. Це просто PWD, it will just show you your path. It's just for convenience. Then you go to this path. Then you go to your folder. In my case, it's bands in GaAs need SOC, spin orbit coupling. And then I copy here my plot. So here was a plot. Yeah, here it is. So I just copy it to my folder. Bands, to the bands folder. To bands folder, and then you have to add some line from the script. You had export library. Here it is. Python 3.6, and then GaAs.
For me, somehow it worked without this line.
Without this line? Then I go to file arsenid to the common calculations, bands. Here I have, and here I just start the same pod. Export from QE script. So you can see this is in the left the common calculation, to the right spin orbital coupling calculations, and you see that here in here some bands became like double bands, like for example this band in K, and here maybe you see in gamma the biggest difference in gamma point, because this band, it now not goes to gamma point, so we have this gap. So it we have some name, it calls spin-orbital coupling gap. So because it makes we have here triple degenerated bands, 1, 2, 3, triple degenerated bands. Now some of these bands are splitting. You see that, for example, this band which goes here, it's actually 2 bands, because here we just can see it, but here it also splits, but not so in so huge amount, because so here is 2 bands, here also 2 bands, because here this spin orbital coupling. And so we have here not 3 bands, but we have 6 bands, and 2 bands, these bands, they goes down, and we have this gap. We have this spin orbital coupling gap, and also we see that all other bands, they also double. Like for example here, this band, you see it slightly doubles. Here we see also the gap, small gap. You see here there was no gap, but here it gaps. It has gap because of spin-orbital coupling, and also it releases the degeneration. For example, here you see it's also gamma point, and we see also this gap. So this spin orbital coupling, one of its features that it's destroys this degeneration. When in some region we have 1 band, but really it's like 3 bands, like in here in gamma point. In reality, it's 6 bands, yeah, but they doubled. Each of them doubled. And of course, this band structure, it's more it is more realistic. And if you will use some experimental tools, you will see this thing. So it's noticeable. You can see it with ARPAS or some other techniques you use. Yeah, for now it is all today.